episode 6 of the Integrate Intelligently podcast from CAD Talk. I am not one of the Brickler brothers. My name is John Thomas. I'm our marketing manager here at CAD Talk. You've perhaps heard my voice on the podcast a little bit so far with the intro and the outro and all that sort of thing. But I'm here today just to get you started with Jeff and Scott. Jeff Brickler, our CRO at CAD Talk. Scott Brickler, our CEO at CAD Talk. Thanks so much for joining us today, guys, for episode 6 here of the Integrate Intelligently podcast. We have been going through our 5 core values: integrate intelligently, relentless reinvention, outstanding outcomes, radical responsibility, and then fast and focused. If you're good at math, you realize that we're now out of core values to talk about, so we've got to start talking about something else. So that's what we're going to be diving into today. We're going to be talking a bit more about what CAD software is. So we'll dive into that here in just a moment. Just a reminder of who we are. CAD Talk is an integration software company helping primarily manufacturing companies integrate their CAD, PDM, PLM software with ERP. You can always visit CADTALK.com to learn more or schedule a demo. Be sure to check out our podcast, other episodes as well. You can subscribe on Spotify, Apple Podcasts, anywhere else that you get your podcasts, as well as you can give us a follow on YouTube as well to watch the video version of the podcast there. The Integrate Intelligently podcast, if you watch us on video, you know we're always recording remotely, but this is the most remote that I think we've been because we're all in 3 different locations today. Jeff, you're in Orlando. Scott, you're in Seattle. Jeff, you're on business for a day more, and then you're going more toward pleasure, I believe.
That's right. Today working, and then tomorrow vacation with the family.
Very nice. Very nice. And then Scott, you are out on business with a deal going out in Seattle with a couple of other folks here from the company, correct?
Yeah, that's right. Actually, then we're out here for Seattle. I'm also happy to see you on the podcast, John. You're representing the hair. Now everybody at CAD Talk is bald, so that's confirmed, which is great. So, but yeah, we're out here in Seattle visiting a new customer that we're really excited about, and then I actually go on a little vacation myself here at the end of the week, and then I'm actually running a Spartan race with my daughter, 10K, on Saturday. So really super excited about that. Hopefully she doesn't leave me behind, and we're not calling a hospital or anything. So it'll be fun though. It'll be a lot of fun.
That's fantastic. So I'm going to be stereotypical here. I've never been to Seattle. Is it raining, and is the coffee good?
Yeah, it is raining. Actually, it's not raining. It's not like just overcast today. It was raining yesterday. We did go down to the very first Starbucks yesterday, which is
okay.
You can actually go visit the very first Starbucks. It's actually within walking distance of the hotel here, and it's. I didn't try the coffee because the line was about 2 hours long to get into it.
Oh my gosh!
It was like probably 200 people waiting to get into the Starbucks to order basically the same thing you get at the other Starbucks next door here. So. Which is, maybe there's something special there I didn't find out, but the really cool place called Pike Place Market had some, there's good seafood, stuff like that, but it's and coffee I've had so far has been pretty good. So
okay, all right. So Seattle is as I expected. That's good to that's good to know. Well, we are talking about CAD software today. It is the Integrate Intelligently podcast. So since I'm on here for at least a few more minutes, I have to share one anecdote about integrating intelligently. Jeff, I shared this with you yesterday. Scott, you haven't heard this yet. So we are recording this right as the front end of the Summer Olympic Games in Paris. So the opening ceremonies were about 4 or 5 days ago now. Watch the opening ceremonies. If you watch them, you know it was a much different take than you usually see on the opening ceremonies. Not in a stadium. It was throughout the city of Paris. Lots of different things going on. It was very eclectic, lots of different things happening kind of all at one time. So I was, kind of sitting there with my wife, Sarah, a couple other folks watching the opening ceremony. And I kind of said to myself, and I turned to Sarah and I said, I've never seen an opening ceremony like this. This is so different. There's, normally this is in a huge stadium, but this is like such a unique take on the opening ceremony. It's all integrated within the city. And Sarah looked at me immediately and said, you have to tell Jeff and Scott. You have to tell them about the intelligent integration that was happening during the opening ceremony. And it did make me think about, Scott, what you've talked about so many times here of I think on one of our last episodes, the complexities of intelligent integration, because the other comment we kept saying was the complexity of this opening ceremony, the production that had to go into it, all of the different moving parts. It's so much more complex than a simple integration. And it felt like this beautiful illustration of exactly what we talk about every week.
Oh, absolutely. That's really cool. That's really cool. It's funny you mentioned there, Olympics. One of my daughter's teammates on her club team got a medal at the Olympics here from Cincinnati. Carson Foster, it's actually one of her teammates on her swim team, which everybody's really jazzed about it. My phone was blowing up when it was happening, so she was super excited. So it's pretty cool on her club team. So congratulations, Carson Foster, for the medaling at the Olympics here, Cincinnati native. So that's really cool.
I actually saw Carson's race and saw Cincinnati pop up on the score there as a Sycamore High School graduate. So very, very, very cool for those who are local to Cincinnati here. Well, anyways, to our discussion for the day, I am, one of the things that we want to do in addition to, looking at the business side of everything with what we do here at CAD Talk is also being able to offer opportunities for education. Because as Jeff has expressed before on the podcast, you kind of hear what we do and it just sounds like alphabet soup. You've got CAD, PEM, PLM, ERP, all these different terms that if you're not in a manufacturing or engineering context, don't mean a whole lot. I am coming from a background that is not those things. So I'm also diving into and learning these things. I'm very much looking forward to kind of decoding the alphabet soup, if you will, and going through some episodes of doing that. We're also getting some guests scheduled as well. So we'll sprinkle these in over the next few weeks and months as we kind of dive into this decoding of the alphabet soup. But for that, as we dive into our first TLA 3-letter acronym, CAD, today, I know it's computer-aided design, Jeff, but other than that, I'm going to turn it over to you to dive through everything with what CAD is, its functions in manufacturing, and why it matters here for CAD Talk, why it's part of our name.
Yeah, that's good. Thanks, John. I mean, it's no secret. I don't think I hide it anymore that I for a number of years, I was a teacher, and I always think about when I came to CAD Talk as a beginner, right, with beginner's eyes and beginner's knowledge. I didn't know anything about CAD, or I didn't know anything about anything of what we did, but I was excited to learn. Anybody who spends a lot of time learning anything knows that vocabulary is critical. How do you talk about something and learn about it if you don't know the words to do it? So I remember thinking, for these podcasts, it'd be great to share some knowledge, right? Some education with the folks who listen, both for our own staff, but also for our families who begin to continue to ask us, what is it that you guys do? But also, I think for all our partners, people we work with, we assume that everyone would know what all these words mean and what they things are. So I thought it would be good for us to talk a little bit about them, not to have a super deep dive like an engineer would be, but to get an introduction to all of these different acronyms, what they do. And so I'm really excited to talk about computer-aided design. So Scott, obviously you have been working these acronyms for many years, and to you they're second nature, probably not even, you don't think twice about them. So obviously we know CAD is computer-aided design. Can you tell us a little bit about what's used for, like who uses it, why does it exist, what's the purpose of it?
Sure. Yeah, I think I went through engineering school in the late 90s and early 2000s, and it was kind of it's the way, I mean, you think about kind of where it came from. It also used to be called computer aided drafting as well. I think that's where the original term was computer aided drafting, because the earliest versions of CAD, I think, were AutoCAD, and some of the other ones were essentially a digital representation of a drafting board, of actually going and drawing something on a board, which I'm actually old enough to have learned that as well, like some of the drafting back in high school and things like that, where you actually use like a compass and a bunch of rulers, and you would create isometric views being like the front, the side, and the bottom view of a part, and doing that manually. And then what happened was they had a lot of technology evolves. It's like, let's take this manual thing that we did and make it digital. So you would actually draw the same kind of line. So AutoCAD in the early days were like, you would use it almost like a drafting board to actually make the same kind of isometrics. And then over time, then you got into doing things that were more object based, like 3D modeling and things like that, where you're actually creating a virtual replica of something in 3D space, and then taking that, and then the drawings and things just became a byproduct of that kind of object in space. But yeah, I mean, computer started out as computer-aided drafting, and then it turned into computer-aided design, and then that's where the world kind of evolved to over time. It's really sophisticated today. I mean, we have things with VR and all kinds of extensions of that we see today that are super important.
So is computer-aided design or computer drafting? Is that so? We have two different types, right? We have 2D and 3D.
Mm-hmm.
Does 2D still exist, or does everybody switch to 3D? Or are there contexts where 2D is still valuable?
Yeah, you see a lot of 2D still out there. I mean, there's a ton of it. I think you see a lot more of it in the architectural space as well as like civil things like that. So I was actually looking at like house plans the other day, and a lot of those house plans come in like floor plans still come in 2D space, but they do 3D representations of them now because people in 3D is more how we see things in the world. So a lot of people can't read 2D drawings; they're kind of abstract. So by having the 3D renderings of those, it allows people to kind of visualize things more clearly and then understand that. But 2D is still quite common. I mean, especially when you think about actually making something, like if a person's reading a drawing or seeing how it makes something, they still, even though a lot of things are built in 3D model space, they're still presented a lot of times in 2D isometrics or 2D views, so people can break those down into actually how to make them. So that still 2D is very much a thing. It's just whether or not they start in 2D or they're generated from a 3D. It's kind of where things are today.
Okay. And is to the users of CAD, are they just engineers, just manufacturing, or like who uses this software? Is it just like design engineers who just make products? Who else could use these things?
Well, CAD's better. I mean, think about it. Even people who, architectural design, construction, all of these different, anything where you had to have a representation of a real life thing in some kind of document format, right? So anytime you're using those types of physical objects, buildings, structures, things like that, all of that would be, even electronics and electrical systems and things like that, plumbing, all that stuff is used as CAD to represent some abstraction of reality so we can talk about it, plan it. It's a lot easier to change and manipulate and talk about paper, something on paper that's a representation or abstraction, than it is to deal with a real thing in real life. So it's like we talk about that specs for software. It's easier to change a spec, which is a paragraph, than it is to change code. It's exactly the same thing. It's even worse when you think about physical objects. You can work out the details and work out the kinks when it's just digital or paper, and then that's your plan. That's your representation for how you're going to build something in the future. So it's when you're actually doing physical things, it's a lot more expensive to experiment when it's physical than it is when it's digital or paper.
Yeah. So obviously I'm not a designer. I spent my early career as a school teacher and education and working with people. And I don't design. I can't design a thing. Of course, I've learned how to use the CAD software, the context of integration and what that matters. I learned enough, but I'm no engineer, no designer. Technology's goal, I think, is always to make a job easier. That's the goal, right? To abstract some of the complexity away so that people don't have to do every aspect, every part of the work. And so I guess in CAD, what is CAD? Can you talk a little bit about like obviously CAD first started, as you mentioned, as just a digital representation of a drafting board, right? Literally drawing lines on paper. Now it's digital paper. But how has that changed for 3D CAD? And what does 3D CAD offer us besides the ability to see it in a three-dimensional space? Like what other features of design software, like what does it do for us other than give us drawings that we could produce? And
well, 3D, I mean, the beauty of kind of object-based design or going to 3D, it kind of drove towards what they call modeling, right? So you have a model of something that's real, right? And then and AutoCAD was doing this as well, even with 2D, but like the idea of like building something in virtual space, like something that's not real, but still real in the sense of like it's a true representation of that thing. And when you do that and you build that, and you can assign attributes, or you can assign data to that, like the part number and what it is and what material it's made out of and all these different things, you can assign qualities to that. And as CAD's gotten more advanced, especially 3D CAD, you can even assign like physical properties and things like that to, and you basically have a representation in the virtual world of this real life thing, and then it becomes more real. So you're able to see things like as time is on. It's not just a picture to make it. It's now something that has attributes that can be based in math, and then in physics. So we can start saying, well, if I apply heat to this, what does this thing do? If I apply pressure to it and forces, how does the physics work? And we're able to kind of model reality in this virtual world, so we know how things are going to react before they actually get into a critical situation. So you think about, and I think a huge driver of that was the aerospace industry, or the space industry. Aerospace, I guess, would be the industry is that where mistakes are really, really costly, right? You can't. So they needed to have a way to model reality as close as possible in the computer, so we could know what's going to happen to this thing when we actually do it. And when human lives are in play and things like that, or cost billions of dollars or cost, how do we know what's going to happen when it's exposed to 5,000 degrees, or when there's this force coming from a direction you didn't expect? I mean, I remember one time here in Cincinnati, or at least in Cincinnati back home, their GE makes aircraft engines, and they would actually make these aircraft engines. And like one of the things that people don't realize is that they birds go into the engines all the time. So I remember them like trying to simulate the birds going into the engines and what would happen to the impellers and all this kind of thing. And then, of course, they would test all that and have an idea of what that would be in virtual space, and be able to make a lot more progress on that design well before they actually tested it in real life. And I remember they actually would take frozen turkeys and throw them in the engines to see what happened. And they actually tested it in real life. But it was amazing how, think about how much costlier that would have been, and how much they were able to learn, and iterate so much faster by doing this in the virtual space. And that's kind of how computers do. They speed up things. They speed up the innovation. They allow you to do things that would take you years and do them in minutes and seconds and things like that. So that's really the idea of like, how do we represent something in a 3D world, and 3D being how we actually see the world is more realistic than, and actually assigning more properties to it and actually making it actually model real things. That's the way that it's going to more and more in the future.
So that's helpful. I mean, I understanding that you're simulating it digitally rather than building, right? Because one way to model something, I think and you can model anything yourself, build models at home, right? Make tests at home. You watch Mythbusters, and they did things to scale. And so the 3D modeling helps us to do that. But how does that, obviously, once you get it modeled, like how do you translate that into to make it, right? Like it's one thing to say, oh, here's this digital thing, right? Maybe it has attributes. Okay. It has a description and a part number, maybe a kind of a quantities of what makes it up, but that's all abstract, right? Nothing's real. How do you take that idea of something in design and then turn that into like a guy, somebody making that thing, right? How do you get there? Because otherwise, like that design is just it's like a picture, right? It's just something that you see on a screen.
Absolutely. I mean, a lot of times people, since there's models, those 3D models and the drawings and such are essentially representations of reality. You can, a lot of times those actual models and things like that are used from which to program machinery to then to actually make things. So there's something called CAM, which is another acronym, computer-aided manufacturing, which usually takes the CAD designs and uses those to create essentially a tool path for a machine to make the part. So it could be typical machines would be lathes, saws, vertical mills, horizontal mills, things like that. And what you can do is they usually start off, and most of the machines, like 3D printing be the exception, most machines create parts through some kind of removal of material process. Yeah. So you might take a design, say you were going to create a flange or a block with holes in it. You might cut the block off of bar stock, and then put it on a mill and drill the 2 holes, tap them out for screws. Those are all removing material from which to create that. And that material, that tool path to do that, in order for the machine to actually do that work, or the machine that is created by starting with the CAD design and then backing it up into a more simplified representation, and then creating a tool path to then mill that material away to make that part. Now, the other aspect of that would be which is 3D printing, would be to have the final result, and then what they do is they actually slice that design up in little individual slices, and then that gets loaded into another CAM software, which then, when the 3D printer goes, it actually goes and draws every slice all the way up until it 3D prints that design all the way up from that, layer by layer by layer. So that's additive manufacturing, which is completely different. It's a newer technology, but because almost everything prior to that, as far as making something, always required the removal of material until 3D printing came around. But the starting slot is always CAD. The final representation of the thing you want, which is then reverse engineered into a tool path or to a layering type of thing to create the final.
It really sounds like that. I mean, the way you describe it sounds like 3D modeling was kind of not the linchpin, but was the force multiplier to allow a lot of other manufacturing processes to become more automated, to become not just automated, but even more technologically advanced. Because once you have that model and you have all of that data attached to it, you can do so much more with it. Does that seem like an accurate statement?
Yeah, because especially if the model's it's just a picture. It's just not like a representation, like a drawing of something. Somebody's freehand drew something. Well, this is kind of what it looks like, a design, to get an idea of what it would look like. These models are they are the exact measurement of that thing. Like that, it's down to whatever the tolerance is. So all the tolerance data and exact measurements, all of that is built into that representation of it. And then all that intelligence is built into all the math, everything that's built into that model can then be used to calculate everything else, like the tool paths and it'll even tell you information like, well, I need to make it on this machine because this machine can hold a tighter tolerance, because that tolerance of that dimension has been specified as data or metadata as part of that design. So not only is it like I can see what it looks like, it actually holds inside of it how it should be made and what the specifications of how it should be made are built into that model as well. So we're just getting into where we're embedding more and more intelligence into these virtual representations of reality, so we know then we can automate more and more of how it's made. And that's kind of like CADTALK works too, is we're leveraging that data to then figure out like how to drive it towards the cost data out of it, how to create routings, how to do all these things that we do downstream of the manufacturing process. We're driving all that by using as much of that data that's been programmed or that's been modeled or put into it by the engineering teams, and using that to leverage and create the downstream processes and things like that. So that 3D representation, the model, the intelligence built into that during the design is just capturing more of the engineer's mind during that process than just a plain drawing used to capture.
So do you think it's easier to be an engineer today than it was 100 years ago?
I think it's different. I wouldn't say it's easier. I think that the complexity is definitely more. There's more things to work with, right? You have more materials, you have electronics, you have computers, you have AI, you have all these things so the diversity of the tools have gone up, right? Now the individual steps, is it easier to create a drawing of a angle bracket than it was 100 years ago? Absolutely. I mean, you could probably create an angle bracket and create drawings for it, the same drawings that somebody created by hand, 100 years ago. You could create those in about, maybe 10th time. It's very, very fast. But are we comparing apples to oranges, really? I mean, you also could do the entire FEA analysis, which is like failure analysis and heat analysis and how it's going to work under stress. All that math that we used to do is probably easier because the computers are helping you do it, but you still have to make the decisions and you still have to make the design and figure out where to start. It's just a lot of times with technology, it just makes everything faster and more convenient.
Yeah. So I guess this is like, we always talk about how manufacturing's gotten cheaper, right? Goods are cheaper. I guess we always assumed that it was always labor, like when we outsourced to cheaper countries, or it was always about labor. But it sounds like really manufacturing's gotten cheaper because some of these tools, right? These tools made it easier, less expensive to to figure out complex things to do more with less. And it sounds like technology, CAD software being one of them, and also the other products that we work with are some of the foundations of what makes delivering products to customers, any kind of products, right? Whether they're speakers for you to listen to or large industrial equipment that mines or produces other gas, for drilling for oil or for gas or any of those kind of industrial products for farming, right? There's all these products that people don't think about every day, but those have to be manufactured. It sounds like the advancements in engineering, right? CAD specifically, this software really just allows very complex tasks, allows them to be done quicker and more easily, and more accurately, and so therefore makes manufacturing cheaper because all the cost of designing is less now. Does that seem? Am I on the right track there?
Oh, I think you're absolutely on the right track. I mean, like one of the defining characteristics of being human is creating tools. We create tools. That's how we're not the strongest, animals. We're not the biggest. We're not any of those things, but we are the best at creating tools to help make things faster and better. And we've got hundreds of thousands of years of creating tools and making things better. And that's all this is. It's like we just keep creating them every day, and CAD is one of them. So that's why as you create better tools and you're able to do more things, less time, the costs go down, right? Efficiency goes up, and that's how we're able to have this abundance of the world we have today. I mean, we were able to create things that 200 years ago, kings couldn't have paid up all their money to get, and we can get them today, for very little money. I think about that today. Like, think about your phone in your pocket is more advanced, is so many hundreds of times more advanced than they had to go to the moon. Right. And we pay $100 for it. And they spent billions, in today's dollars to do that. And we just keep creating better and better tools. And CAD just one of them. Yeah.
Right. Yeah. It makes sense. I mean, when you're not working in manufacturing, you're not supporting manufacturing companies, you always hear, like in the news or whatever, manufacturing is getting cheaper, products are getting cheaper. And then it's, never really think about, well, how does it get cheaper? Like, what are the steps to get cheaper? And of course, there are many steps, right? There's not one thing that just automatically makes everything cheaper. It's a bunch of different tools, as you said, that make the whole process faster, cheaper, more efficient, better.
And one thing I always like to share that I think is pretty remarkable. It always gets me very excited to think about what we do and everything. It's like, I used to travel a lot, and we used to visit places. I've been to where they make like army tanks and aircraft carriers, all the way to the place that makes the ovens that toast subs at Subway. I've been to all these different kinds of places, and one thing that you're at all of. You think about everything that you interact with on a daily basis is manufactured somewhere. Like everything, it's kind of remarkable. And you think about the sheer volume of things that you like. Remote control or this desk that I have in this hotel room, it's made somewhere. And there's a company who makes that thing, and somebody designed it, somebody thought of it. It started in someone's mind, and now it's reality. Everything that we have started in someone's mind, and now it's a reality. And it's why manufacturing is such a cool cornerstone industry to be part of and to help, is because it's just so core to everything we do in the world. It's like everything we do interact with is manufactured somewhere, and sometimes we forget that. We just kind of take it for granted. Like there's this thing that we can use, but there's somebody somewhere who thought that thing up, put it in some kind of design, and they had to create it so we can enjoy it. It's pretty remarkable. Yeah.
Yeah, man, it really is. I mean, of course, buildings that are hundreds of stories tall, all the way down to small, headphones that we put in our ears, to large destroyers and ships and tanks, but also, lots of capital equipment, lots of equipment that, like, the people who pick your strawberries use, or people who get grain. I mean, all kinds of different products that you don't even see on a day-to-day basis. All of those things have to be manufactured. They have to be created, right? Somebody does. I think about one of my first customers. They make vibratory equipment, and it was really cool when I visited them 9 years ago. I remember going they're in between Chicago and Milwaukee, and they would make these huge vibratory equipment. They would sell to like recyclers, and then people would say, well, what are your customers? What do you do at CADTALK? Because everybody would ask me, and then I'd say, well, we sell software, we help companies, and what do those companies do? I said, well, there's one company that we support. They make like this giant equipment that like your recycling center would buy. So like here locally in Cincinnati, at least, we have a recycling center, and these guys come into the trucks. They dump all your recycling in there, and it's all mixed together. You think, well, gosh, how does that work? You think it's like a bunch of people just back in the at the plant goes pick it up, can plastic, and that's not how it works at all. They have these giant machines that they make that shake and vibrate, have these conveyors and these really big machines that really separate all of that stuff and then grind it up and then compress it and ship it off to be reused. And it's a whole production, but somebody has to come up with this idea of how do we separate all of these recycling, right? And so it is really incredible. Like all these things to make our life easier, we don't ever think about. That's what I always loved about it. It was like, it's kind of the unsung hero, kind of the hidden things behind all the things that these people are making that is really important for our everyday lives, but you don't think about because they just, it has to happen.
It's really inspiring, actually. I mean, it's like, you think about it, like in manufacturing, I mean, it affects everyone on the planet. Everyone is working, is something's being manufactured and used by everyone on the planet. I mean, it's so core to being human, and like, so it's a very inspiring industry to work in.
Yeah, I must admit, when I came to CADTALK, I didn't know much about manufacturing at all. But having been here, and what I also loved is just meeting the people who work in the manufacturing companies, the engineers, the designers, the people who come up with the ideas and the new products they're making, and the manufacturing companies that make those things. And it is inspiring. It's incredible. It's like so much is going on behind the scenes that we don't even think about. That's important to our daily lives, that usually the products aren't even bought by us, right? But they are bought we buy products from companies that need help to build their thing, right? And then so it goes. Then somebody buys something else. It's like, I pay for my recycling, and my recycling center has to buy this product to help recycle, right? Help to separate the recycling, and that's the sort of thing, right? Is that you don't even know about those, and so.
I think about all the geniuses and people who have come up with the ideas to make all these things happen, right? I remember there was a genius level engineer I worked with at the packaging machine company I started when he first came out with CADTALK, and he created it. And there was this they had a problem figuring out how to, when they pulled a carton off of they had a stack of like cardboard boxes for cartons, like they had boxes of cereal and stuff. He had figured out a design to pull the carton off the top of the list. And when it pulled it actually opened it, and then it would flip it around, and they would lay it down in the conveyor in a perfectly open square, so then they could push the cereal bag into there. Well, that was a patented design, and it was a motion. It was like a special motion that he had, almost like a figure eight type thing. I'm probably butchering it. If anybody from that company is listening today, but that motion that he figured out and did all the math for to figure out that motion, right, to do that, how they were going to mill that I think it was called orbit track. How they milled that in order to figure that out. Like, I mean, it was like, that's an unsung hero. Think about, like, every day for all these little boxes of tissues, cereal, everything that's been created. This guy's genius at that design made that more efficient, so we could, and then made it cheaper for people to buy that food and nourish their family. All that stuff was possible because this guy had this genius idea, and he put it down on paper. He put it in CAD.
Yeah, I mean, it's incredible how, like, I think we often think of like these big achievements, right? Like the internet or this really big, or the AI, these really big things. And most of technology is like incremental improvements. It's like, right, it's like what, 1% or fractions of 1% getting better all the time, and just compounded over a long period of time. That really makes a difference. It's that guy who's working and designing and coming with this ingenious idea. You think, well, it's not really that big of a deal. But if you're working on that problem and you're making that just a little bit better, all of those different people, millions and millions of people doing all that, the designs, and they can focus on that work, is that all those together make it incredible, right? Give us small incremental improvements, but multiplied by millions and millions of times.
There's a great book called Sapiens that talks about like the whole like history of humanity and stuff like that. And if you really read that book, it'll really show you like how remarkable it is to be in the world today, and like how things started. Even like language is a huge invention. Like things that we just think about, we just abstract away as simple stuff, and making of tools, and all these different things that somebody had to figure that out somewhere in the history of humanity, right? So
that's it.
Great book. I recommend that because it'll really open your eyes to like, holy moly, look, like what is we have available to us today, and like all the genius that had to come before us in order to get us where we are today. It's pretty awe inspiring, actually. It's really amazing.
Not to get too far down into the philosophical, which you and I love to do. Like, so if you're new to this and you're just trying to learn about CAD software, or you're just like, what would be the takeaways, right? What are the things that someone who is either new to manufacturing or new to, let's say you work with companies, you work with manufacturers, you're not an expert in manufacturing, but you work with manufacturers, or like us, you work with engineering and manufacturing. What are some of the things about CAD that people need to know? What are the kind of bare minimum, right?
Sure.
If you're going to get out of like CAD 101 or intro to CAD 101, what are the things you should know? Like, what's the vocabulary around those things?
I think it's something that's, I would say this, it's not necessarily something that's abstract that like only engineers use. I mean, I think that there's CAD that people use to figure out how they're going to landscape their yard, or how to even like how you're going to put a piece of furniture into your house, right? All of that is actually, I mean, I think there's a feature that you get from Amazon that way you can see like how you can actually take the image of the table you're going to buy, and you're going to see how it looks in your room. Like CAD enables that to happen. That's how they're able to do that. You probably use CAD in ways you didn't even realize. And like,
right.
I mean,
you probably use CAD every day. People use CAD every day, but don't even know about it, right? They don't even know it's there.
Yeah. All it really is you think about it being a computer generated representation of this real life thing.
Right.
And that's really all it is.
So what are some of the big names in CAD? Who are the big, if you were going to become an engineer and you say, okay, I want to design something, I want to work in manufacturing, or I want to work with manufacturers. What are the names, the big names that I have to worry about? What are the things I should learn, the vocabulary?
Well, I mean, the big players, are obviously you have your AutoCAD, which is a parent company called Autodesk. You have SolidWorks, I think parent company is Dassault, Siemens, Solid Edge, Creo with PTC. There's tons, which used to be called Pro Engineer. And there's just tons of them. And then you start getting the electrical packages. I mean, there's tons and tons of companies who do this. Those are the big names that are out there. Google SketchUp. I mean, you can go. Actually, what's really interesting, if you, for free, you can go get Google SketchUp and start drawing things on your computer using the browser. Tinkercad. We used to use Tinkercad. My daughter used to use Tinkercad to create 3D models in order to 3D print on our 3D printer. So it's very, very accessible. There's free tools out there to play with and learn and things like that. So, but those are the ones I mentioned earlier, the big players that we end up working with that are, when you're doing it when you're doing it at scale, or you're really doing a manufacturing company, that's what you use. But Tinkercad works great. I mean, you can use Tinkercad to make parts that you can actually use, in a 3D printer. So it's very accessible. Those are the tools.
Yeah, that's good. That's good. I appreciate that. For people who are new, you'll hear like it's mechanical CAD, at least, which is what we deal with mostly. Some electrical CAD, but the big publishers of mechanical CAD include Dassault, and Dassault has a number of products, SolidWorks being one of them, and CATIA. And then PTC has a number of products, Creo and Winchell, as you said, and some others with PLMs. Autodesk has products. But like you said, there are lots of different ones out there, even the free ones, but also very specific ones for a certain like niche manufacturers. Like, there's cabinet ones, and there are ones for structural steel and bridges, and ones for even building boats. There are very
pipes over there. One we had a
Pipes,
customer.
yeah, there are pipe
Some of
ones.
the
There are ones
pipes.
for just
So, yeah.
designing the pipes. Ones for designing, I mean, all kinds of really niche. Like there are more generalized ones that are for good for general mechanical, but then there are ones that are specialized that are very niche, very much used for that. So, but if you're if you're new to manufacturing and new to understanding CAD, really there are some major players out there through Dassault and PTC and Siemens. Definitely a lot of the bigger ones that we see, but there are a number of others. And so what should, I mean, obviously we don't do designs ourselves, and we work with customers who do designs. Real short, what do designers or people need to know about the design? Like how does CADTalk care about that? The design, like what do we need to know about there? What's the kind of key thing that people should think about when they want to integrate their systems, right?
Sure. Yeah. I mean, I think that, like I mentioned a little bit earlier, is that the more the representation or the idea in the mind of the engineer is represented in that 3D model or in that design, the more that we can extract information from which to make decisions or to drive other systems that are downstream from the engineer. And that's really what it comes down to. It's like, can we, transforming engineering intent into manufacturing execution? How do we turn what they thought of, this idea, and then figure out how we're going to make it, how much it's going to cost, and where we're going to, what parts are we going to buy from? All that stuff has to be figured out to actually make a part. The design is just the first step. So all the derivative data and all the derivative processes that have to happen in order to make that go from the engineer's mind into an actual physical thing. CADTalk helps with that, getting those systems talking to get the systems talking so we can actually make that happen. And the more information that's in those representations, the easier it is for us to do that. Yeah.
Yeah. It would be fair that, to say that CADTalk's one of those tools, right? That we talk about humans building. It's one of those tools that make things easier, right? Make things faster. CADTalk's one of those tools that make it a little bit cheaper for people to buy products, right? Because we're helping our customers make products more efficiently, more cheaply, quicker, improve the process the whole way, and such that makes it them more competitive and sell their products to the next customer, and then that customer has more money to invest in improving their processes. It's just down the line, right? So CADTalk's doing just like CAD did its part in a big way to help push innovation to the next level. I mean, CADTalk's doing its small part to make that communication, make that translation happen between the systems, so that the ERP systems to be able to do that. So I think, not to get too more into ERP systems, but I'll come up, I'm sure, in another episode. But what's the difference between a CAD system where you're doing designs, right? It's like everything's there. That's how you make it. What's different about a CAD versus an ERP? Like, why do we need something in one and the other? Why can't we just do everything in CAD?
Yeah, I think that they're different jobs, right? I mean, one CAD is in order to create the digital representation of the engineering's intent, like what they designed it to be. And the ERP, which is, enterprise resource planning, which is a big word, basically essentially means the system from which to do the manufacturing, right? And to track everything. So the ERP does essentially figures out like the steps of not only how are we going to make this thing, what are we going to make it out of, where are we going to buy it, where's it going to go, and all these different things. Those are all that secondary steps. So once the engineering has decided what the hell they're going to do, and they give it a physical representation of it, the ERP is what actually makes the company do everything else. And then also, and then you add the E part of the ERP, because it used to be MRP, then it went to ERP. The E part of it was attaching accounting to that process. So we knew when we make something, how much it costs. It actually costs us to make it. So then we know if we're making a profit or not. And then there's, that we're able to sustain the future. So everything that happens once the engineer finishes the design, that happens after that, a lot of times happens in either, it happens in ERP, which is where we're going to buy it, how are we going to make it, and how much it's going to cost us. That's really what the manufacturing systems do. And and that's just different, as a different, completely different purpose than what the engineer is trying to do, with get the representation out of their mind and communicate it. At the end of the day, just communication.
Yeah, that's good. It's really just different. The guy who's doing the design, or the guy or gal, the person doing the design is different from the person making the thing, right? If you really boil it down to like the basics, right? If I'm going to draw something, I'm going to draw it. Once I get it drawn, if I'm at home, I'm going to make a sketch of how I'm going to do this, and then I go into my garage or whatever, and I hammer it together or put it together, and all good, right? Like when we were kids, our dad get the saw out or get in the welder, and we're going to make this thing, right? We'd hardly draw it, but the person who would weld it up or cut the material and do all that, it's a different person from the guy or the gal, the person who is going to actually design it. And so since they're different, they have different jobs to do. They have different tools to use, software tools in that respect.
And a lot of these things are just there to do things to scale, right? I mean, Brent, like you've mentioned this in the past. It's like, if some of these things would be necessary, think about how humans would have had blacksmiths. Blacksmiths would have had an idea in his head, and then he would need to forge the metal and create the thing that he wanted to create. He could skip a lot of steps, but when you start making, say he's making swords or whatever it is, you making 2 or 3 swords a week. That's not a big deal. When you're making hundreds of thousands of these things, and you have hundreds of people working on them, communication becomes a thing. You got to get that done. And these systems allow you to communicate across. It basically cuts down on the communication cost. You add more humans, you decrease the communication cost. So if I'm an engineer, I have a vision in my mind of how this thing is supposed to be built. I can communicate that vision by creating a CAD model and communicating that to another person who can take that and match what I was thinking in my mind and match it to reality. And we can scale. Then ERP systems will help you scale it up and create processes to create hundreds of thousands of things. That's why everybody on the earth can actually interact with manufactured goods, because we figured out how to scale it up. And these systems help us do that. They help us scale things up.
Yeah. So I guess at the end of the day, like all these softwares, CAD, they're all communication tools, right? Even CADTALK, it's a communication tool between. Now what we do is we communicate between 2 different systems, but essentially they're all communication tools so that we can communicate with each other on a standard language. So we can each, as you said, scale up and be able to do all of that.
Yep, absolutely.
Well, man, this was a great conversation. Very interesting, philosophically speaking, with manufacturing, but also I think, just an introduction to why computer-aided design is what it is, like why it's important, and how manufacturing companies use it. So, Matt, again, I really enjoy these kinds of discussions. It's exciting to really celebrate the customers, really celebrate the people making the stuff every day. Gives me a new appreciation for what it takes to keep our world going.
Absolutely, it's really inspiring. It really is.
Okay, well, Scott, again, thanks a lot. I appreciate it. This wraps up our episode on computer-aided design and CAD systems. Thanks everybody for joining today. So again, you can look us up on Spotify or anywhere your podcast is. You can get your podcast also on YouTube. You can also visit us at CADTALK.com. Really, encourage you to subscribe to the podcast and give us a listen.